In this video, we will explore how we can use an algebraic tool, something called a partial fraction decomposition, typically just PFD, to evaluate the integral of rational functions. So, as a reminder, this is something that you'll hopefully encountered when you're in a pre-calculus course, but a rational function is much like the example that we see here, which is a polynomial. So in this case, think x minus 9, divide it by another polynomial. And typically, if we were to look at maybe integrating a rational function, a polynomial over a polynomial, that looks like it could be a difficult example. We haven't encountered this yet. But a partial fraction decomposition allows us to take a rational function and break it up in terms of simpler rational functions that are easier for us to integrate. And if we were to have this partial fraction decomposition to start, we could very efficiently evaluate this antiderivative. We would have the antiderivative of 2 over x plus 5 minus the antiderivative of 1 over x minus 2. The first antiderivative would be 2 ln absolute value x plus 5. And the second one would be the natural log of x minus 2. And when it comes to using partial fraction decompositions to integrate rational functions, typically the largest amount of work is going to come in the algebra portion of the problem, finding that partial fraction decomposition. So let's talk about how we go about doing that. This slide contains the basic guidelines for determining a partial fraction decomposition. And I'll kind of hit on the basics, but of course we'll illustrate this through several examples. So the first thing to consider is comparing the degree of the polynomial on the top and the degree of the polynomial on the bottom. If the degree in the top is bigger than or equal to the degree in the bottom, we will call the rational function improper. And in this case, as we'll see in our first example, we will need to do a polynomial long division. Then, if the degree in the top is smaller than the bottom, that is what we call a proper rational function. What we would do is factor the bottom. And something we learn about in pre-calculus is when you're factoring a polynomial, you can factor it into linear terms and irreducible quadratics. That would be quadratics that do not factor. And how you can tell that is the discriminant, the thing underneath the square root in the quadratic formula, the b squared minus 4ac is negative. And the typical example that we might encounter for these irreducible quadratics would be things like x squared plus a number. So maybe x squared plus 1, x squared plus 2, 3, whatever it might be. So for each of the linear factors, if we have ax plus b to the nth power, for each power of that ax plus b, the first power, second power, third power through the nth power, you will have a term in the partial fraction decomposition. Similarly, for the irreducible quadratics, if it's raised to the nth power, you have a corresponding term for each of those. But because it's a quadratic, we balance that out in the top by making it constant x plus a constant. So b1x plus c1, b2x2 plus c2, and so on. And that should be an n and an n. Now let's illustrate this through some examples, and we'll see the first question is writing out the form of the partial fraction decomposition. Then the next question will be performing the algebra to solve for those unknown constants. So we're going to start off just by writing down the form of several partial fraction decompositions. So in this first function, we have a rational function, degree 3 in the top, and if we kind of count up 3 plus 2 plus 1, degree 6 in the bottom. It is a proper rational function. Corresponding to the 3 linear terms in the bottom, x, x plus 2 squared, x minus 1 cubed, we have some number of terms in our partial fraction decomposition. So we have x, then just going through each of the factors, and we have x plus 2, then we have x plus 2 squared, then we have x minus 1, x minus 1 squared, and x minus 1 cubed. So in that partial fraction decomposition, there will be a single term corresponding to each and every factor in the denominator. And because these terms all correspond to linear pieces, they get a single constant above them. So big A, B, C, D, E, and F. And we would call this the form of the partial fraction decomposition. If you wanted the actual partial fraction decomposition, you would need to do the algebra to solve for these unknown constants. And we'll see that in our integration examples. So in this second example, we have a linear term and a single irreducible quadratic. So each of those terms correspond to one term in the partial fraction decomposition. Above a linear term, we put a single constant, so just a big A. And above any irreducible quadratic, we put a constant x plus c. Similarly, in our third example, we have a linear term, but then this repeated irreducible quadratic. So we think the partial fraction decomposition contains a term for each one of those factors. So along with x squared plus 1, there would be an x squared plus 1 squared. Then we add in the constants. Above a linear term is a single constant, and above an irreducible quadratic, there's going to be a constant x plus a constant. So bx plus c, dx plus e. Okay, so let's move on to some examples. Let's evaluate the integral of x cubed plus x over x minus 1. Now, going back to the guidelines for the partial fraction decomposition, we need to start by comparing the power of the polynomial on the top divided by the one in the bottom. So degree 3 is bigger than or equal to degree 1. So before proceeding to a partial fraction decomposition, we need to do a polynomial long division to rewrite our integrand function in a more reasonable manner. So let's just do that to the side. We have x minus 1 divided into x cubed plus x. And it may have been a while since we've done this, so let's remind ourselves how this works. We look at the x term out front that we're dividing with, and we ask ourselves, x goes into x cubed how many times? Well, x times x squared is x cubed. So in the top portion here, we add an x squared. Then we take the x squared, we multiply it by the x minus 1, and whatever we get back, we subtract. So we would be subtracting away x cubed minus x squared. And the key here is to always be careful of distributing this minus sign through. You have x cubed minus x cubed, which goes away. Then you have a negative of a negative, so positive x squared, and then plus the x we originally had. And we keep playing this game until what we get in the bottom is something that it has a degree smaller than what we're dividing with. So x multiplied by what is x squared? X. Then we subtract away x times x minus 1. So x squared minus x. So x squared minus x squared is 0. X minus a minus x is 2x. And we keep going because we want to make sure that the remainder we get has a smaller degree than 1. So x times what is 2x? 2. So we subtract away 2 times x minus 1. So that'd be 2x minus 2. And what we end up with is a 2. And this is the point we know to stop the polynomial division because 2 has smaller degree than x minus 1. And what all this information tells us is if we take x minus 1 times x squared plus x plus 2 and then add 2 to it, we get back x cubed plus x. So let me just go ahead and write that down. So what we've learned is that x minus 1 times x squared plus x plus 2 plus the remainder term is equal to x cubed plus x. And what we would like to do, thinking back in terms of our integral, is come up with a more convenient way of expressing x cubed plus x over x minus 1. So we have our x cubed plus x. Let's just divide every term by x minus 1. So when we do that, we have the x squared plus x plus 2 plus 2 over x minus 1 equals x cubed plus x over x minus 1. And we've now done exactly what we need it to do. We have a more convenient way of expressing x cubed plus x over x minus 1. So we plug that into the original integral. So the original integral becomes the antiderivative of x squared plus x plus 2 plus 2 over x minus 1. Once we've done this algebra, it almost works out too good to be true, because now when we look at our integrand, each of the 4 terms we see, we can easily anti-differentiate. Just an observation to make is typically this term that we get from dividing here is going to be something that would require a partial fraction decomposition. So typically there might be another step in the problem. So anti-differentiating, we would have 1/3 x cubed plus 1/2 x squared plus 2x plus 2 ln of the absolute value of x minus 1 plus c. So as a reminder, when it comes to integrating rational functions, polynomial over polynomial, if the degree in the top is bigger than or equal to the degree in the bottom, we need to do a polynomial long division. So let's look at an example where we do not need a polynomial long division. So in this case, we have a degree 1 over a degree 2. So in order to integrate this, we are going to do a partial fraction decomposition. We're thinking it's this algebraic tool. So if we factor the bottom, which we can always do in terms of linear and irreducible quadratics, x squared minus 1 is a difference of squares, so that would become x plus 1, x minus 1. So the form of the partial fraction decomposition is 2 linear terms, so that would be a over the first one, x plus 1, plus b over the second one, x minus 1. And if we can determine what the values are for the constants a and b, we'll easily be able to integrate this function. And how we will always go about working this is we look at it and think from an algebraic perspective, what portion of this equation is making it difficult to work with? It's the fact that we have fractions. So we take our denominator on the left and we multiply every term by it. So on the left, when you multiply by the denominator, you have just a 5x minus 1. In this first term, when you multiply by x plus 1 times x minus 1, the x plus 1's cancel, and you're left with a times x minus 1. And in the second term, when you multiply by that denominator, x plus 1 times x minus 1, the x minus 1's cancel, and you have b times x plus 1. And the idea here is you want to find the values of a and b that are going to work for any choice of x. So to determine a and b, if it is possible, we can use intelligent choices for x. And corresponding to every linear term, there will be an intelligent choice that we can use. For example, let's observe, if we plug in x equals 1, the a term goes away, and we can solve for b. So let's do that. If x is equal to 1, the left-hand side would be 5 minus 1, which is 4. On the right, the a term cancels, and we're left with just b times 2. So 4 equals 2b implies that the value of our constant b is 2. Similarly, if we let x be equal to minus 1, that will make the b term cancel. So if we plug minus 1 into the left-hand side, we have minus 5 minus 1 is minus 6. And you have a multiplied by minus 1 minus 1. And the b term cancels. So minus 6 equals minus 2a implies that a is equal to 3. So putting this together, we have our partial fraction decomposition. So the function we're integrating we can write as a over x plus 1 plus b over x minus 1. And as we mentioned earlier, now that we've done this partial fraction decomposition, kind of the algebraic step, the resultant integral should be fairly reasonable to evaluate. So in this case, it's going to be 3 natural log absolute value x plus 1 plus 2 natural logs absolute value x minus 1 plus c. And now a few general observations related to the partial fraction decomposition, which recall is usually the part of the problem that requires the most amount of work. So when you write out the form of the partial fraction decomposition, it's going to contain a single term for each factor of the denominator, when you write it in that factored form of linears and irreducible quadratics. In order to solve for the constants, what we should do is clear fractions. So you take the denominator of the original function and you multiply both sides of the equation by it. Once you do so, you want to plug in as many intelligent choices of x as you possibly can, and there will be one intelligent choice at a minimum for each of the linear terms that is present.